This presentation was prepared by Dr. Nima Mahdian. All right, today we're going to embark on a pretty fascinating journey. I want you to think of yourself as an investigator, and your data, well, that's the crime scene. Your mission is to find the true story that's hidden inside all that data, to build a model that's not just close, but is actually correct. We're going to move way beyond the usual suspects in the simple methods to uncover the techniques that really separate a flawed guess from a principled, truly reliable model.
So here's our roadmap for this investigation. First up, we're going to uncover a fundamental, critical problem with a very common method that a lot of us use. Then, we'll equip ourselves with some seriously sophisticated solutions to fix it. And finally, we'll learn the principle of judgment. How to choose the absolute best model when you have multiple, pretty good candidates staring you in the face.
Okay, so first things first, we have to understand the scene of the crime. We're going to take a look at a tool that many of us know and probably trust, the standard least squares method. And we're going to discover a hidden weakness, a flaw that can lead us completely, totally astray.
We're going to start with a familiar friend, the linear least squares method. Here, we're applying it to what's called an ARX model. Now, that's just a fancy way of saying we're trying to predict the current output, y of t, using a combination of past outputs and past inputs. It's pretty straightforward. We bundle all that past data into a vector we call the regressor, phi, and all the unknown things we're trying to find into a parameter vector, theta. The whole goal is to find the theta that makes the error between our prediction and the real output as small as possible. And the least square solution gives us this really direct, elegant formula for it. On the surface, it seems absolutely perfect.
But, and this is a huge but, there is a critical, often unspoken assumption here. For least squares to actually work the way it's supposed to, the things we use to predict our regressors have to be completely uncorrelated with the random noise that's hitting the system. But just look at this diagram. In any dynamic system, the noise from yesterday, E of t minus 1, influences yesterday's output. But wait, yesterday's output is part of today's regressor. This creates this nasty circular link, what we're calling a forbidden correlation. The very noise that we're trying to filter out is actually baked into our predictors, and that is a huge problem.
And this, right here, perfectly illustrates the consequence. The least squares estimate becomes biased. It's like having a world-class marksman who has a perfectly steady hand. All their shots land in this tiny little cluster, but they're aiming at the wrong target entirely. The estimate is precise, sure, but it's fundamentally inaccurate. So here's the crucial point. This is not a problem you can solve by just getting more data. Look at the formula. That bias term doesn't disappear even if you have an infinite number of data points. It is a systematic error that's baked right into the method itself.
So, how in the world do we solve this? Clearly, our basic tool just isn't up to the job. We need to bring in something more sophisticated. So let's explore solutions like the instrumental variables method, or IV, which is designed specifically to handle this exact kind of corruption in our data.
The new strategy is actually conceptually pretty brilliant. The original least squares method fails because it's trying to make the prediction error orthogonal to our tainted regressors. So the new idea is, well, what if we force that error to be orthogonal to a different set of variables? A special set that we'll call instruments, designated by zeta here, that we can guarantee are clean and completely uncorrelated with the noise. Now, for this to work, our instrument needs two key properties. It has to be relevant, meaning it's strongly related to our original regressors, and it has to be exogenous, meaning it is totally independent of that process noise.
And this simple idea leads us right to the instrumental variable, or IV method. Now, take a look at the formula for the IV estimate. It looks almost identical to the least square solution we saw just a few minutes ago. But notice that one crucial change. One of those tainted regressor vectors, phi, has been swapped out for our clean instrument vector, zeta. That one simple substitution is incredibly powerful. As you can see in the diagram, it completely severs that corrupting link between our estimation formula and the noise. And the result? Well, as we get more and more data, our estimate now actually converges to the true parameter. We've achieved what's called a consistent estimate. Now, the power of this whole IV method really hinges entirely on our choice of instrument. It's kind of an art. The simplest path you can take is to just use past values of the system's input, since those are typically independent of the process noise. But for a lot more power, we can use what's called an auxiliary model. This is a more sophisticated technique where we first build a sort of preliminary model just to generate a set of ideal, totally noise-free instruments. Let's break down that more advanced technique because it is incredibly clever. It's this three-step bootstrap process.
So first, you compute an initial simple ARX model using just standard least squares. Now, we know this model is probably biased, but that's okay for now. Second, we use this flawed model with only the input data to generate a completely simulated noise-free output. You can think of this as the output our system would have produced if there was zero noise. And then third, we construct our final instrument vector using past values of this clean simulated data. The result is a perfect instrument that is highly correlated with our real system, but by its very construction is completely uncorrelated with the real system's noise. It's really slick.
But hey, we have to be honest about the trade-offs here. No tool is perfect. The main advantage of the IV method is huge. It's consistent. It solves that bias problem that plagued least squares. It's also pretty simple, computationally. But on the downside, the estimate can have a higher variance, which means it might be a bit more spread out around the true value. And we have to be really careful about the weak instrument problem. If our chosen instrument isn't strongly correlated with our regressors, the math can get unstable, and that can lead to a very unreliable estimate.
Now, for more complex models like ARMX models, where the noise itself has its own structure, we need an even more advanced tool. This is where pseudo-linear regression, or PLR, comes into play. You can think of it as an iterative, next-level version of the IV concept. It's this clever bootstrap procedure that turns a complex, non-linear problem into a sequence of simpler, linear IV problems. As you can see in the loop, it starts with a guess, creates instruments, solves an IV problem, and then uses that new solution to refine its instruments and just does it again and again until it converges on a solution that estimates both the system dynamics and the noise characteristics at the same time.
Okay, we've done it. We've mastered the techniques to get a consistent, unbiased estimate of our model parameters. Awesome. But in doing so, we've actually created a brand new dilemma for ourselves. We can now generate many different, totally valid models. So the question becomes, how do we judge which one is truly the best representation of reality? This graph right here is the heart of our new problem. As we make our model more and more complex, by adding more parameters, that solid orange line shows that our error on the training data will always go down. A more complex model can always wiggle more to fit the data points it's seen. But here's the crucial question. Is this a real improvement, or are we just fitting our model to the random noise in that one specific dataset? This is the overfitting trap. The dashed line, our validation error, shows us what's really going on. At first, more complexity helps. But then, eventually, the validation error starts to creep back up. So the whole game is finding that sweet spot, that optimal model that perfectly balances this trade-off. The solution is to stop guessing and be principled about this. We need a formal method for making this judgment call, and the answer comes from something called information theory, in the form of selection criteria. The core concept, which is beautifully illustrated by these scales, is that we have to balance two things. On one side, we have a fit term that measures how well the model explains the data we see. But on the other, we have a penalty term that punishes the model for its complexity. The best model is simply the one that minimizes the total of these two terms, the one that achieves that perfect balance.
So let's meet our first principled judge, Akaiki's Information Criterion, or AIC. You can think of AIC as the pragmatist. Its main goal in life is to find the model that's going to make the best possible predictions on new, unseen data. It's all about performance. Now look at its formula. You've got the goodness of fit term on the left, and then a really simple penalty term. For every single parameter D you add to your model, AIC slaps on a fixed penalty of 2. That's it. It's a very straightforward rule for a very practical goal. Our second judge, the minimum description length principle, or MDL, it's more of a purist. It comes from a totally different perspective. It frames this whole problem as one of data compression. It asks a really deep question. Which model provides the absolute shortest description of the data? The best model is the one that achieves maximum compression. Now, its penalty term is different. Notice it includes log of n, where n is the number of data points. This means its penalty gets stricter and stricter as you collect more data. It punishes complexity much more heavily than AIC, especially for big data sets, because it's on a quest to find the simplest, most plausible, true underlying system.
So let's put them head to head. This comparison is absolutely critical for any practical work. AIC has that constant penalty. MDL's penalty, on the other hand, grows with your data size, making it way stricter, and this leads to their different objectives. So, here's the rule of thumb. Use AIC when your goal is purely predictive performance. You just want the best possible forecast, and you don't care that much if the model is a little more complex than the true system.
Use MDL when your goal is to identify the most plausible, simplest underlying structure. You really want to know the true order of the system. So the key takeaway here is that neither one is universally better, they just answer different but equally important questions.
And here it is, the complete investigator's field manual. This brings every single thing we've talked about together into a practical 5-step workflow. You start by preparing and inspecting your data. Then you do some initial analysis to get a feel for the system. Step 3 is where you use a consistent method like IV to estimate several different candidate models. Step 4 is the judgment phase where you calculate AIC and MDL for each candidate to select the best one. And finally, and don't skip this, you have to validate your chosen model on a separate dataset to make sure it truly works. This right here, this is your map to success.
So we've journeyed from a fundamental flaw to sophisticated tools, all the way to the principles of sound judgment. You now have the complete workflow to move beyond those biased estimates and to build principled, reliable models. So the final question isn't for me, it's for you. What story is your data waiting to tell?